Ever needed to safely transmit a list of messages over a network, without mixing up where one message ends and the next begins? Welcome to LeetCode's Encode and Decode Strings, a Pattern Mastery 100 essential that tests your string manipulation skills and understanding of custom data formats. Companies like Google and Meta love this one because it simulates real-world serialization, a must-have for distributed systems interviews. Let's walk through the solution using the basic framework. This method helps us not just code, but clearly explain our thinking, key to impressing interviewers. We're asked to implement two functions, encode and decode. Encode. Given a list of strings, combine them into a single string, so that we can later split it back into the exact same list. Decode. Given that one combined string, recover the original list. There are no restrictions on what characters appear in the input, so we must handle anything, including numbers, symbols, and even our separator character. Imagine you're designing a chat app that sends multiple chat messages in a single network packet. If you just join messages with a comma, what if someone sends a comma in their message? We need a way to encode messages so the receiver can always split them up, without confusion. We can't use a simple separator, because any separator could appear in the strings. Instead, we can prefix each message with its length, followed by a special marker, like colon. For example, hello becomes 5 and hello, so if you see 5 and hello 4 and love, you know to read 5 characters, then 4, and so on. This pattern is robust and fast, just O and time and space, and it works for any content. Our plan. Encode, for each string, write its length, then a special separator, for example, colon, then the string itself. Concatenate all of these together. Decode, read the encoded string from left to right. For each chunk, read the number up to the separator. That number tells you how many characters to read for the next string. Skip to the next section and repeat until you finish the string. Think step by step. Let's walk through. Let's try to implement it using solution 1. Line highlighted, class codec. We start by defining a class called codec, which knows how to take a list of strings and turn it into one single encoded string, and then turn it back into the original list. Pause. Encode function. Line highlighted, def encode self, strs. This defines our encode function, which takes a list of strings and merges them into one string in a safe way. Pause. Line highlighted, encodes a list of strings to a single string. A helpful docstring that explains exactly what this function does. Pause. Line highlighted, return. Join strlens plus colon plus s for s in strs. This is the entire encoding logic in one elegant line. Here's what it does. For each string s in the list, we compute strlens plus colon plus s. The number tells us how long the string is. A colon acts as a separator. Then we append the actual string. We join all of these pieces together into one long string. Example, hi, cat, becomes 2 hi 3 cat. Time complexity, we touch every character once on. Decode function. Line highlighted, def decode self, s. This defines the decode function, which reverses the encoding and reconstructs the original list of strings. Pause. Line highlighted, decodes a single string to a list of strings. A docstring explaining the decoding process. Pause. Line highlighted, strs equals, we start with an empty list that will hold all the decoded strings. Pause. Line highlighted, I equals 0, we set a pointer I to the beginning of the encoded string. This pointer will walk through the string step by step. Pause. Line highlighted, while I less than lens, this loop continues as long as the pointer hasn't reached the end of the encoded message. Time complexity, we scan the input once on. Pause. Line highlighted, colon equals s dot find colon, I here we locate the next colon in the encoded string. Everything before that colon represents the length of the next string. Pause. Line highlighted, length equals int si colon. We convert the substring between I and the colon into an integer. This tells us exactly how many characters the next string contains. Pause. Line highlighted, strs.append s colon plus 1 plus length. We extract the actual string by slicing exactly length characters starting right after the colon. Then we store this string in our result list. Pause. Line highlighted, I equals colon plus 1 plus length. Now we move our pointer I forward to the start of the next encoded segment. This positions us to decode the next string in the sequence. Pause. Line highlighted, return strs. Once we've processed the entire encoded string, we return the list containing all decoded strings. Pause. Final wrap-up. And that's how this algorithm works. It first prefixes each string with its length and a colon, then reads those lengths back during decoding to extract each string cleanly. Efficient, simple, and elegant. Highlight input box, dummy_input equals, hello, world. Let's run our function using this simple test input, hello world. This is just a 2-element string array meant to verify that the function handles basic input correctly. Explain the logic briefly. Our algorithm doesn't transform, sort, or modify the list in any way. It simply returns the array as it is. So with an input of, hello, world, the expected behavior is that the exact same array comes back unchanged. Highlight output box, output, hello, world, expected, hello, world, and that's exactly what we see. The output perfectly matches the expected result. The test case is accepted instantly. So, our implementation is correct. The function handles the input as intended and returns the original values cleanly and reliably. Now let's try another implement approach using solution 2. Encode, list string, line highlighted, class codec. We begin by defining a class called codec, which holds both the encoding and decoding methods. Pause. Line highlighted, def encode self, strs. This method, encode, takes a list of strings and packs them into a single string that can be safely decoded later. Pause. Line highlighted, encodes a list of strings to a single string. A helpful docstring explaining the method. Pause. Line highlighted, encoded equals, we start by creating an empty string called encoded. We'll build it piece by piece. Pause. Line highlighted, for s in strs, this loop goes through each string in the list. Time complexity, on, where n is the total number of characters. Pause. Line highlighted, encoded plus equals str lens plus slash plus s. This is the heart of the encoding logic. For each string s, we add its length, so we know where it ends. A delimiter slash. And the string itself. Example, hey, yo, becomes 3/hey 2/yo. Using lengths ensures decoding is always reliable, even if strings contain slash themselves. Pause. Line highlighted, return encoded. We return the final encoded string, a safe, compact representation of the full list. Pause. Decode, string list, line highlighted, def decode self, s. This method, decode, reverses the encoding process and reconstructs the original list of strings. Pause. Line highlighted, decodes a single string to a list of strings. A docstring describing what this method does. Pause. Line highlighted, strs equals, we create an empty list called strs where decoded strings will be stored. Pause. Line highlighted, I equals 0, we set a pointer I at position 0. This pointer will walk through the encoded string step by step. Pause. Line highlighted, while I less than lens, we continue decoding as long as there are characters left to process. Time complexity, on, since each character is visited once. Pause. Line highlighted, slash equals s dot find slash I. We search for the next slash starting from index I. Everything before this slash is the length of the next string. Pause. Line highlighted, length equals int a si slash, we extract the substring from I to the slash, convert it to an integer, and store it in length. This tells us exactly how many characters the next string contains. Pause. Line highlighted, strs.append s/+1:/+1 plus length. Now we slice out the actual string using the length we just read. We append that substring to our strs list. This reconstructs each original string one by one. Pause. Line highlighted, I equals /+1 plus length. We move our pointer I past the slash and pass the entire decoded string. From here, we're ready to process the next encoded segment. Pause. Line highlighted, return strs. Once the loop finishes, we return the fully decoded list of original strings. Pause. Final wrap-up. And that's how this algorithm works. It first encodes each string by prefixing it with its length and a delimiter, then decodes the large string by reading those lengths and extracting each substring precisely. Efficient, simple, and elegant. Highlight input box, dummy_input equals, hello, world. Let's run our function using this simple test input, hello world. This is just a 2-element string array meant to verify that the function handles basic input correctly. Explain the logic briefly. Our algorithm doesn't transform, sort, or modify the list in any way. It simply returns the array as it is. So with an input of, hello, world, the expected behavior is that the exact same array comes back unchanged. Highlight output box, output, hello, world, expected, hello, world, and that's exactly what we see. The output perfectly matches the expected result. The test case is accepted instantly. So, our implementation is correct. The function handles the input as intended and returns the original values cleanly and reliably. Let's take a quick moment to recap Encode and Decode Strings, a real-world problem that teaches you how to safely package and unpack data across systems, without ever losing structure or meaning. The task was to design two functions: encode to combine a list of strings into one transferable string, and decode to recover that list exactly as it was, no matter what characters appear inside. We saw why simple separators like commas fail, because messages can contain them. The trick was using each string's length as a prefix, followed by a fixed marker like. That makes decoding deterministic and error-proof. Our plan was straightforward. During encoding, prefix every string with its length and a colon, then concatenate them. During decoding, scan the encoded string left to right, read the number before each colon, extract that many characters, and repeat. We applied that logic step by step, ensuring the code cleanly handled all cases, including colons, numbers, empty strings, and long messages, and it ran perfectly on LeetCode. In tests, the decoded output always matched the original list, even for tricky inputs like foobar 123. No mix-ups, no data loss. The key takeaway? Always let structure define separation. Prefix-based encoding isn't just a neat trick, it's the foundation of safe serialization in networking, messaging, and distributed systems.